Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the video conferencing system, the infrastructure that powers every video call, webinar, and virtual meeting you join. We'll cover WebRTC, SFU media routing, signaling, turn relays, recording, and the trade-offs that make or break real-time conferencing at scale. Whether you're preparing for a senior engineering interview or building collaboration infrastructure, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the video conferencing system, the infrastructure that powers every video call, webinar, and virtual meeting you join. If you have ever wondered how platforms like Zoom, Google Meet, Microsoft Teams, or WebEx handle hundreds of participants in a single call, share screens, record sessions, and stay smooth even when someone's network is terrible, this video is for you. We will walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FAANG interview or building real-time collaboration infrastructure, let's get into it. Here is the core problem. Modern video conferencing must make real-time audio and video feel natural across a global, heterogeneous internet. Every participant has a different device, browser, operating system, network bandwidth, and latency. Some users are behind strict corporate firewalls or network address translators. Others are on mobile networks with rapidly changing packet loss. The system must also support screen sharing, chat, reactions, recording, and breakout rooms, all while keeping end-to-end latency low enough that conversation feels natural. A single bad routing decision can cause choppy audio, frozen video, or a dropped call, which destroys user trust. The business needs a scalable, resilient video conferencing platform that adapts to network conditions, scales to large calls, and remains secure and easy to operate. Let's walk through the functional requirements. First, the system must allow users to create and join meetings through a unique meeting identifier or link, with authentication, waiting rooms, and host controls. Second, it must transmit real-time audio and video between participants using WebRTC, with support for mute, unmute, video on and off, and device selection. Third, it must support screen sharing and presentation mode, so one participant can broadcast their screen or a single application window to others. Fourth, it must provide a signaling layer to coordinate sessions, negotiate media capabilities, and manage peer connections. Fifth, it must provide recording, either locally or in the cloud with search and replay. Sixth, it should support chat, reactions, hand-raising, and breakout rooms. These capabilities define the user-visible surface of the platform. Now the non-functional requirements. The system must be low latency. Audio and video should stay within roughly 200 to 400 milliseconds end-to-end, because anything higher makes conversation feel stilted. It must be resilient to packet loss, jitter, and bandwidth changes, using adaptive bitrate, forward error correction, and jitter buffers. It must scale horizontally to support millions of concurrent meetings and thousands of participants in a single large webinar. Security matters deeply. Media must be encrypted. Meetings should be protected by passwords, waiting rooms, and role-based access, and recordings must be stored securely. The system must be interoperable across web browsers, desktop clients, and mobile apps without requiring plugins. And it must be cost-efficient, because real-time media is expensive to relay and store. Here is the high-level system architecture. On the left, clients connect from web browsers, desktop apps, and mobile apps. They first talk to the web application and authentication service to schedule or join a meeting. The signaling service then coordinates the WebRTC handshake, exchanging session descriptions and IC candidates between participants. The selective forwarding unit, or SFU, is the heart of the media plane. It receives one audio and video stream from each participant and forwards the appropriate streams to the others, saving enormous bandwidth compared to a mesh topology. A turn server relays media through firewalls and NAT when direct peer-to-peer or client-to-SFU paths are blocked. Media streams are optionally sent to a recording service that stores them in object storage. Chat and presence live on a separate real-time messaging layer. The analytics pipeline collects quality metrics for operations and debugging. The key metrics to memorize: cold end-to-end latency, usually measured in milliseconds, with 150 milliseconds or less feeling transparent and 400 milliseconds feeling like a delay. Packet loss rate, the percentage of media packets that fail to arrive, which directly degrades audio and video quality. Jitter, the variation in packet arrival time, which must be absorbed by jitter buffers. Bitrate and resolution, which adapt to available bandwidth. Frame rate, typically 30 frames per second for smooth video. Audio quality score, often modeled as mean opinion score. Time to first frame, how quickly a participant sees video after joining. CPU and memory usage on the SFU, because relaying many high-resolution streams is computationally expensive. And call drop rate, the fraction of calls that terminate unexpectedly. These metrics are what the operations team actually watches. Let's trace the end-to-end user journey. A product manager opens the calendar invite, clicks the meeting link, and lands in a web browser waiting room. The host admits her, and the client requests microphone and camera permissions. The signaling server assigns her to the meeting session and exchanges SDP offers and answers with the SFU. ICE negotiation finds a media path, falling back to the turn server if her corporate firewall blocks direct UDP. Within a few seconds, she sees and hears the other participants, and they see her. The product manager shares her screen, and the SFU rebroadcasts that video track to everyone while muting her camera feed. The host records the session to the cloud. When the meeting ends, the recording is processed, the SFU tears down the media connections, and participants receive a follow-up email with the recording link. The core models and algorithms. The media routing model defines how the SFU decides which streams to forward and at what quality. Simulcast sends multiple resolutions from each client, so the SFU can choose the best layer for each receiver based on bandwidth and layout. The signaling model manages the WebRTC session lifecycle through join, offer, answer, ICE candidate exchange, and leave events. The congestion control model continuously estimates available bandwidth and adjusts bitrate and resolution using algorithms like Google Congestion Control. The ICE framework selects the best network path among host, server reflexive, relay, and peer reflexive candidates. The recording model demuxes audio and video streams into a synchronized container for storage. The security model applies encryption, key management, and permission checks. The key trade-off is quality versus bandwidth. Higher fidelity requires more bits, but aggressive adaptation keeps calls smooth under poor networks. Now the low-level design deep dive. The signaling service is built as a WebSocket or Socket.io cluster with rooms as the unit of session state. Each room holds participant metadata, media capabilities, and role assignments. The SFU is a media plane service that exposes RTP endpoints, maintains one upstream transport per publisher and one downstream transport per subscriber, and uses an RTP router to forward packets. It supports simulcast and scalable video coding, so that a single sender can produce multiple layers consumed at different qualities. The turn server runs on a public IP and relays UDP traffic when symmetric NAT or firewalls block direct connections. Recording workers subscribe to the SFU as hidden participants, receive audio and video, and mux them into MP4 or fragmented MP4 for storage. The Quality Analytics Service collects RTCP receiver reports and client metrics to drive adaptive bitrate decisions and post-call diagnostics. Key takeaways for your interview. First, always start with WebRTC and explain why it is the dominant real-time transport. Peer-to-peer for small calls, but almost always an SFU for production conferencing. Second, be ready to compare mesh, MCU, and SFU architectures, and explain why the SFU dominates modern systems. It saves upstream bandwidth and allows flexible layouts. Third, signaling is not media. Keep the signaling path separate and describe the offer-answer dance clearly. Fourth, turn is not optional at scale. It is the fallback that makes calls work behind corporate firewalls and NAT. Fifth, security is part of the design, not an afterthought. Encryption, meeting permissions, and recording protection all matter. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for the video conferencing system. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the video conferencing system. We covered the full picture from WebRTC and the SFU through signaling, ICE, turn recording, and the low-level design of the media pipeline. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.